It's a pleasure and honor to present state-of-the-art developments in agricultural robotics, focusing on robotic harvesting. I will be presenting Sweeper, sweet pepper harvesting robot that we developed as part of an EU project, and I will focus on lessons learned and challenges ahead as much as time will permit. This is Sweeper.
To build the first sweet pepper harvesting robot, that was the goal of the Sweeper project. Increasing the efficiency and reducing labor dependence will ensure Europe's high-tech greenhouse food production yields and competitiveness. The robot is an assembly of an autonomous mobile platform with a robotic arm holding an end effector for fruit harvesting. The robotic arm with the end effector scans the crop for mature peppers. The camera operates completely independently from surrounding light conditions. It gives color images and a distance map. This information is used for pepper detection, localization, and maturity classification. Peppers are scanned by looking slightly upwards. By observing the bottom part of the pepper, maturity can easily be detected.
Okay, agricultural robots are being developed for many different agriculture tasks, such as cultivating, harvesting, pruning, spraying. However, despite 30 years of developments in agricultural robotics, very full robotized systems are only scarcely available. The commercial robots, we have the robot milking robot, we have some field crops robots going back and forth along the field for spot spraying, for some cultivating tasks. Other than that, all these neat developments are in research only. And the main reason is that the agricultural domain is one of the most complicated domains for robotic systems. The environment is unknown with very high variability. It is a very unstructured environment, a lot of dynamic changes along the field, along the season, even along the same day. It's a very tough environment which requires robust systems. It has high humidity, very high temperature sometimes. It has to deal with dirt. In addition to the complex environment, an agricultural robot must deal with a high variability in the objects. Objects are of biological nature and inherently are different in color, shape, texture, location. I cannot model in advance where the objects will be. As you see here, I have on the same plant 3 different maturity levels. The crop, the objects are collided. There's a lot of obstruction, branches, leaves. Illumination change continuously along the season, along the day. I have sometimes the sun is directly illuminating, sometimes I'm in totally dark. And in addition, I'm dealing with a very cheap product, so I cannot justify a very expensive robot. Agriculture, robotics, it must deal with both complicated objects and complicated environment. And in addition, it has to deal with a very fragmented environment, object, and task force. If I need to develop an agricultural robot for each of the type of crops, look how many different crops I have. And this requires special intelligent sensing and grasping algorithms for each specific. Additionally, we developed the sweet pepper harvesting robot, where we develop it for several cultivars only. Look at the big difference between objects, sizes, colors, location. I have many different environments. A robot for watermelons and melons will be totally different for robots for apple harvesting. Greenhouse conditions, I have plants on one side, I have mushrooms where I'll develop a robot to pick from the top. And even if I'm dealing within the greenhouse, the robot has to depend also on the task itself. Roses, I want to cut from the bottom of the stem. Clusters of tomatoes, I need to harvest just at the end of the cluster. So this creates a very complicated task. The sweet pepper harvesting project robot, what we started, it was a 4-year Horizon 2020 project, which started at the outcome of crops. Crops was an EU project also, which focused on developing a multitask platform, focusing on the modular elements. We developed a platform that was aimed to harvest apples, sweet peppers, and grapes, and also for site-specific spraying. We started the sweet pepper harvester from this project, coming into with the insight that we should develop a focused robot designated for sweet peppers. There was no commercial available robot on market. In addition, we selected for sweet peppers, since this is a very high value crop, a very complicated crop, very dense, non-uniform maturity. And of course, greenhouse cultivation is already highly standardized, which allows for introduction of robotics. The focus of the project was intelligent sensing and grasping. We decided not to focus on the manipulator, not to focus on the platform. However, we decided to focus on crop design. This was a new aspect of the project not dealt with before in agricultural robotics. The concept was that in addition to dealing with the robot design, we should try to optimize the crop for the robot. And I will focus on that a bit later. We had a growers advisory board, which was involved in the project from day one, and they were very important in directing the directions of the research. And in addition, we aimed that the robot would be integrated with the logistics, so once developed, they could go into the system very easily. The sweeper project was one of the main developments, as I said, was developing the robot for different crops. Along the season, we evaluated performance for many different cultivars, and we selected the best cultivars that would fit the robot. The 2 best cultivars were the one that you see here. In addition, we went intensively into investigating into different cultivation practices. For example, concentration of CO2 is known to decrease leaf surface. We evaluated the system in different growing conditions regarding illumination. By means of color, we could control and influence the plant morphology. And also, we could influence and create longer stems, which helps us with the actual harvesting, cutting, by increasing misting. So these were just some examples. For more details, you are welcome to look at one of our papers in biosystems engineering. And as you see here, the results that we received were 61% success rate, with cycle times about 24 seconds per fruit. However, I must note that 50% of this time was dealing with logistics, with dealing with moving along the row and with discharging the fruit after harvesting. So this can be in the future improved. Now, just to put this in perspective, when we came into the project, if you look at the different robotic harvesting projects that dealt with a wide spectrum of different fruit, as you see here, most of the robotic harvesters were aimed at tomatoes in greenhouses, oranges and apples in orchards, but there was also a wide spectrum. Cycle times on average were 33 seconds, from a very few seconds to over 100 seconds. So the 24 seconds is realistic and is within the scope. And harvest success rates were on average 66%. So the harvest success rate of sweeper is a good achievement. Now, if we look into 30 years of robotic harvesting, These are some of the results, that outcomes from it. Ripeness was dealt with only in 22% of the research. So in Sweeper, we dealt also with ripeness. We did not deal with, as I mentioned before, in designing the optimal platform. And as I will soon show you, this is critical and this should be dealt with. In most cases, sensors were almost off the shelf. One of the best robots, and I'll pinpoint on here, and this is some of our insights, one of the best robots is the Kiwi harvesting robot with only 5.5 second cycle times and 51% success rate. In this robot, they dealt with a novel robot design and a novel gripper design. The robot design itself was a low-cost system, which was very effective, and this improved both the success rate and cycle times. And the gripper design had a very interesting aspect, and I invite you to look into it. So if we look into 30 years of agricultural robotics R&D, technical feasibility has been proven. We have proven that we are able to detect the fruit, reach the fruit, grasp the fruit, and move it to a container. However, performance is still limited, both in cycle time and in success rates, and the economics are not out there. Very few papers, research at all, dealt at all with the economics. And basically, there's no commercial harvesting robot out there. So let's see what is needed in order for it to become a reality. These are some of our robotic projects in which we develop site-specific sprayer, date sprayers. You're invited to look at our internet site in order to see it. But I just want, from those projects, from the Sweeper project, some of the lessons learned are that in order to succeed, you need to simplify the task, enhance the robot, and define requirements. And I'll just very briefly go into some of them. Simplify the task can be done in 4 different directions. First direction, modify the cultivation system. And as I showed you in crops, you can use a single row versus a double row. You can use, as you see here in the apple orchards, make a very thin apple orchard in order to be able to view the fruit better. If you look at the strawberry harvesting robots, if you deal with a harvesting robot that has to harvest from the ground, it will be very complicated, versus if you use this cultivation system where you just go into the greenhouse and you see the robot, you see the strawberries, it will be very easy. You can use alternative cultivation practices. So instead of developing a fruit that I have 4 different maturity levels on one cluster, let's have a fruit that ripens at once. Let's have a fruit that the fruit do not grow in clusters. This will simplify the process. In addition, we can do breeding. And as we mentioned, we definitely did some breeding in the in the Sweeper project, and you are invited to look at how we did the selection of the optimal breeds. In addition, you can use different supportive mechanisms. You can use a blower in order to blow the leaves away. You can use, and you are invited to look at our paper on flash, no flash. You can use a flashlight in order to overcome the external lighting. And by subtracting the images, you can improve your detection very strongly. Additional work can be done in enhancing the robot. For example, using multiple sensors to overcome the limitations of a single sensor. Using advanced algorithms, deep learning algorithms, which have just been introduced. Active perception. Most of the reports to date are on single perception, not dynamic perception. Dynamic perception is able to improve the performance. You can use learning, and this is just recently being introduced into agriculture in order to learn from experience and apply it to a new crop, to a new field, to a new task. Human-robot collaboration can, of course, increase the performance by integrating the human into the loop. And you can see some of our work on teleoperated robots or human and robots operating together at different levels of autonomy. A very important idea that can be conveyed and should be conveyed and has been proven successful, as I showed you in the Key robot, is developing intelligent, smart design, specialized hardware. And here are just some examples. I guess a very neat example, and you can look them up, is Tavel Agrobotics, developing small flying robots in order to harvest the apples. And you can develop different and explore different robot designs. Here are just some ideas which could be further explored in agriculture for intelligent sensing, for intelligent grasping. However, last but not least are the requirements. Technical requirements must be considered. As I mentioned, we started from the sweeper project, from the crops project, which is a multi-task robot. I would say this is a no-go. It is much preferable to design a special robot for a special task. It will be much better fitted, will much perform better. You can increase the redundancy in the system and make smaller units which perform better. Additionally, you must design the robot to fit the sensing and to fit the crop. Here you see an example of a gripper, one of the first grippers for the sweet pepper harvesting robot, which was a no-go, an excellent gripper, which works fine, developed by Festo, but it works fine only if the sensing is 100% correct. And since the agricultural environment is very complicated, sensing is not 100% correct, and the localization is ±2 centimeters. And therefore, this gripper on the top left side is a no-go. Because if I'm ±2 centimeters, I cut the fruit, I cut the plant, I cut the stem. And therefore, we went ahead and developed a basket gripper, which gives us redundancy in the location. In addition, maybe it's better for us to develop robots that do not perform for 90% success rate. Let's develop robots that perform only for 50% rate. They will be cheaper, and then I can have 4 robots instead of 2 robots that are performing at 90% success rate. And of course, we need to take into account also the safety aspects, ethical aspects, usability aspects, social aspects, and as I mentioned before, integrated with the logistics. So if I want to sum up a take-home message, you need to develop an optimized robot. It has to be a KISS design, keep it simple. Smart is stupid. It has to be simple, and it of course has to be safe. However, you must also optimize the crop for the design in order to create an affordable design which is sustainable and includes the human and is aims at the human and is accepted by the human. We must remember that we're designing our robots today for agriculture in another 10, 20, 50 years, and they will look different. Agriculture robotics in 2050 will look at agriculture in 2050, which will be not the conventional fields that we have today, but perhaps different cultivation practices, and therefore we must take this into account when we are developing the agriculture robot. So thank you very much. You can see many more details on the Sweeper website, on our Intelligent Robotics Lab here at BGU website. I would like to thank all my students who have contributed to the many different developments, and thank you for your time.